Today's my lecture topic is axial flow turbines. The axial flow turbine, like its counterpart, the axial flow compressor, has flow which enters and leaves in the axial direction. There are two types of axial turbines. One is impulse type, another one is reaction type. The impulse type turbine has its entire enthalpy drop in the nozzle, therefore it has a very high velocity entering the rotor. A reaction turbine divides the enthalpy drop in the nozzle and the rotor. The axial flow turbine also depicting the distribution of the pressure, temperature and the absolute velocity. Most axial flow turbines consist of more than one stage. The front stages are usually impulse, that is zero reaction, and the later stage have about 50% reaction. The impulse stages produces about twice the output of a comparable 50% reaction stage, while the efficiency of an impulse stage is less than that of a 50% reaction stage. The high temperatures that are now available in the turbine section are due to improvements of the metallurgy of the blades in the turbines. Development of directionally solidified blades as well as the new single crystal blades with the new coatings and the new cooling systems are responsible for the increase of firing temperatures. A high pressure ratio in the compressor also causes the cooling air used in the first stage of the turbine to be very hot. The temperatures leaving the gas turbine compressor can reach as high as 1200 degree Fahrenheit. Thus, the present cooling schemes need revisiting and the cooling procedures are in many cases also quoted. The cooling schemes are limited in the amount of air they can use before there is a neglecting an effort of in overall thermal efficiency due to an increase in the amount of air used in cooling. The rule of thumb in this area is that if you need more than 8% of the air for cooling, you are losing the advantage from the increase in the firing temperature. The new gas turbine being designed for the new millennium are investigating the use of steam as a cooling agent for the first and second stages of the turbines. Steam cooling is possible in the new combined cycle power plants, which is the base of most of the new high performance gas turbines. Steam as part of the cooling as well as part of this cycle power will be used in the new gas turbines in the combined cycle mode. The extra power obtained by the use of steam is the cheapest in the available. The injection of about 5% of steam by weight of air amounts to about 12% more power. The pressure of the injected steam must be at least of about 12% more, that is at least 16 psi, that is 4 bar above the compressor discharge. The way steam is injected must be done very carefully so as to avoid compressor surge. These are now not new concepts and have been used and demonstrated in the past. Steam cooling, for example, was the basis of the cooling schemes proposed by the team of United Technology. High turbine temperature technology program was investigating firing temperatures of 3000 degree Fahrenheit in the early 1980s. The development of new materials as well as cooling schemes has seen the rapid growth of the turbine firing temperature leading to high turbine efficiency. The stage 1 blade must withstand the most severe combination of temperature, stress and environment. It is generally the limiting the component of the machine.